just under a month ago.
Okay, the lecture today is I should say, very strange way to look at two-dimensional classical oscillation, and that is to use almost precisely the tools of the quantum mechanical analog, which involves spin-a-half, or two-level systems. The two-level systems that everyone is talking about in the quantum information field as a hope for being able to build quantum computers. So this is where classical mechanics overlaps with some very modern quantum mechanics. So the first thing we're going to do, after just a quick one-slide review of our Lagrangian approach to oscillators that we've done in the last lectures, I want to immediately go into the analogy that exists between the first order in time differential equation of Schrödinger, which works for virtually all of quantum mechanics we know right now, including relativistic quantum mechanics. Compare that to our classical 2D harmonic oscillator. It's a second order differential equation involving a K matrix, and connect it to the H matrix, the Hamiltonian matrix that quantum mechanics uses. And this will involve the spinor symmetry, but actually I call it Hamilton-Pauli. Pauli comes much later with something that behaves like spinors. Hamilton's the one that invented quaternions, and that's the way we'll approach this. It's hard to get away from that Irishman. He's done so much. So we'll see again today one of his most great achievements. In any case, we're going to have something called the ABCD theory of both of these sides of the analogy. And what we're going to do is derive an exponential evolution operator that's analogous to the just the plain exponential we talked about in chapter 10 of Unit 1, which you remember. So now we're going to generalize that. And the other thing we're going to talk about is detailed properties of that exponential operator with spinors in the exponent. A couple of things that are really quantum mechanical, but we treated classically, nuclear magnetic resonance Hamiltonian. You'll see that we're dealing with that. And then the whole idea of Euler angles, and I have a machine here that is, we call the Euler angle machine, that will help you visualize that, and the the exponential, which we call the crank operator, because it's an analogous to the crank on this device that's sitting on the table that we'll get to. So this business with these we call A, B, C, and D operators generalizes, and the next lecture, which I'm going to maybe break into at this point in this lecture, has a review section that's this lecture, but then there's some other things that we should maybe get a time to look at in this particular lecture. And the battery is charged up on the camera, so we may be able to do that. Okay, so here's what we did before. It's basically a Newton's equation for a spring mass system that's completely characterized by K constants, the spring constants, and also a mass matrix. We're going to get rid of that very quickly here, so we'll be doing with just a second order differential equation with something that's proportional to a unit matrix that is a symmetric Hamiltonian. Then we're going to discuss the symmetries that are available in the quantum mechanical side of this analogy. Okay, so this is what we got to in the last thing, and remember the eigenvalue here of this K matrix is the square of the eigenfrequency, because we are dealing with a second order time differential here. That's not going to be the case with the quantum mechanics, which is a first order time differential equation. In that case, the operator that we'll be dealing with, the H operator, Hamiltonian operator, eigenvalues are directly the eigenfrequency. Okay, so here's the deal, and I'm going to do this on, actually going to switch over and get the other screen here to run the same lecture. Then we'll maybe pick it up later on. And so what we're talking about right here, and it's kind of off the edge on this one, is a 2x2 permission. That's the requirement if you're going to do the quantum mechanical equation in order to conserve the probability, the sums of squares, absolute squares, components of a two-dimensional vector. So we're going to start obeying the rules of quantum mechanical dynamics that satisfies the transpose matrix has to be the conjugate, complex conjugate of its JK, KJ relation across the diagonal. So these number here has to be the conjugate of that number. So there are only two parameters to describe the diagonal of the Hamiltonian, two real parameters which we call B and C. And we'll give lots of reasons, mnemonics to go with those letters. And then A and D, asymmetric diagonal, that's what they'll stand for. They're real, have to be real, in order to satisfy this demand for a Hermitian matrix in quantum dynamics. Okay, so let's go ahead on this, and I just noticed that I tried to erase something here and I didn't succeed. Review of lecture 23. We're on lecture 22 right now, so we've got to get rid of that. Anyway, enough confusion here without having something like that. In any case, one of the things to notice here is that the Hamiltonian, which has 4 parameters, A, B, C, and D, has the same number of parameters, that is 4, as the state. And the way we're going to characterize the state is just kind of like the way we characterized it for the two-dimensional oscillator. There'll be a real part, which is a coordinate for the first component, and then there'll be an imaginary part, which is the momentum for the first coordinate and then the second coordinate. So there's 1, 2, 3, 4. That's basically 2 plus 2 parameters for this state. And that means that there's a direct mapping of the 4 parameter states to the 4 parameters of an operator that describes the state. But that's getting a little ahead of what we want to talk about here. Basically, the relationship is that these are 4 parameters because it's 2 times 2, 2 to the squared, and this one is 2 plus 2. So there's 2 ways to do 4. And 4 is the number of space-time dimensions. So there's some very deep numerology that's going on there, which we will maybe talk about later. In any case, I want to separate the real and imaginary parts of this equation here, and then I want to make the connection very precisely with the, this is all real, parts of the Newton's equation for the oscillation, that is the second-order differential equation. So we're going to be converting this first-order complex equation into pairs of real first-order differential equations. That is 2 pairs. So there are going to be 4 real equations that come out of this thing, and we've got to map them onto this one. We're going to go through the detailed way of doing that involves the Hamilton equations. Then I'll show you a really simple way to do this at the very bottom of this discourse here. So here it is written out with everything, every variable, a real or imaginary part of something, and we need to connect that with the first order differential equations that result. Okay, so in this case, what I have here is an x dot. That's the imaginary part. So I'm going to connect this x dot here to all of the things that come out of the imaginary part of the result of multiplying this matrix by this vector here. So you see the A times x1 plus B times, with an I x, let's see if that's right here. Well, we've got an I here, so I'm doing an I x1 here, and then a minus P1 here when I put that I on there, and I'm putting the dots on them, so that it looks like kind of equation 2 they use for classical mechanics. And so forth. And in any case, the result is that this x1 dot here is a linear combination of these real parts. The two momenta, 1 and 2, and then the second coordinate. And then, again, the momentums 1 and 2 multiplied this time by the B and D, and then a plus C, and now the first coordinate multiplied by this parameter C. So the deal is that these are four equations that you probably don't see in a quantum mechanics book, but they're there. And with higher dimensions of quantum mechanics, they'll be obviously more. If you're going to n dimensions, you'll have 2n equations. So here, I'm going to start with a classical Hamiltonian designed to give the results that we have just written down there. And this is what it is. It's kind of a weird oscillator equation in which I have a parameter outside of the parentheses, a single parameter to describe both mass and spring constant. And so this is just a whole P1 squared plus x1 squared multiplied by a half, and then this parameter A. Same thing for the second component. Then there are two couplings that result from or that we need in order to make this marriage of these two equations. And this one right here just involves the cross products, x1, x2 coordinate, and then p1, p2. We've had this one already in our coupling with the K matrix. We didn't see that one. And then this is really weird here, where we have a product of space and momentum. That's something we definitely didn't have in this one. And then these two just are a funny way to rescale this one, sort of like the Estrangian thing, where you make the dimensions and the momenta of the same ilk. So I'm going to do Hamilton's equation on this thing. That is, we know that x dot is partial h with respect to p for first coordinate and second coordinate and any classical coordinate. And then p dot is minus the derivative, partial derivative, with respect to the coordinate, just the coordinate by itself. Here, no dots on it like the Lagrangian. And then another minus sign, same thing for the second component. So I go through on this equation and apply the Hamiltonian, assuming, and this is really important, that you aren't messing with these parameters. That would be parametric amplification. Everything goes crazy when you do that. We'll talk about that at the very end of this unit. But right now, those are constants. As were these spring constants in here. The parameters were held constant, so they are also going here. Okay, well, let's put it on the other screen here. That's where we are taking the Hamilton equations and noticing that x1 dot that I got over there, surprise, because it's designed to do that, is the x1 dot that I have over here, and the same with all the other three canonical variables. Okay, so that is kind of neat. Now, what can we do with that, and how can we understand it better? That's what we need to talk about before we really get into this. But anyway, you see, we've got a marriage. Whether it's consensual or not, we have to work that out. But we've got one, and I'm just basically going through here and taking it apart in such a way that I make a second order differential equation. So I do a second derivative to get x1 dot dot. That means I dot every one of these things in the x1 dot equation and look for what their values are. P1 dot, we've already got that, so I stuff it in here and do the same here with the P2 dot. And then there's an x2 dot with this crazy C. That's something we didn't see happening in our K equation. So we've got something extra here that this equation over here doesn't have, and we'll explain that in a minute. In any case, writing all of this and then going ahead and doing the same with x2 dot, turning it into x2 dot dot, and stuffing in the appropriate variables for the velocities, if you will, of the first time derivative. So here's what it boils down to. It boils down to almost something that has the form of this K matrix that we talked about before. Okay, so what we're doing here is we're really looking at an equation like this. There's the K matrix. Okay, perhaps different values for those two, and maybe different values for those two. That's something that better not happen here, and sure enough, it doesn't happen, so we're in business there. But this is just for c equals 0. C is a weird parameter here that this one doesn't have. So for c equals 0, there's a pretty easy thing that happens. This I partial derivative with respect to time, which is equal to this operator here, that is the time derivative, is this A, B, B, D matrix. Remember, we left the C out. And that is being turned into, you see, the square, you see, of the I partial with respect to T, which is the matrix squared. So this is the easy way to do all this. Okay? And the question is, does it work for C? This is for C equals 0. Okay? You simply take the Schrodinger operator, which is the derivative with respect to time, times I, that's H, the square. Okay? So, that's sort of the first thing. But, and then the idea is it then becomes, this thing is the square root of the Newton-Hooke equation. Dot dot equal K matrix. That's the K matrix right there. K matrix is the square of the Hamiltonian. And it works if you turn the C back on again. Now what the heck's the C? Remember when we started doing cyclotron resonances? Okay? And we used complex numbers to help do that? That's what the C is. The C is adding the effect of a magnetic field, or effect of an external rotation, or something that has chirality. And that's really what the C stands for. All of these parameters have lots of nice mnemonics, and you know how I love to do that kind of stuff. Okay, so just to review again, we can just see this thing as a square of the H operator. That's the square of I times the time derivative. I get a minus the second derivative with respect to time is equal to the square of the operator A, B, B, D. And then if I do a B minus IC and a B plus IC, it works as well. So that's where we stand now. We have something to play with. All right. Now, this is where we start saying, well, you know, I could have just solved this the way the quantum mechanics do and just do an exponential of this operator minus IH, and I'm off to the races. That's kind of true for this one, too. And as you'll see, because this analogy is perfect, for constant parameters, we can't do that. But what I want to do now is have I think, a memorable or easy to remember derivation of all the things that have to do with spinors. And the spinor arithmetic is a generalization, but it is like complex arithmetic, and so is the spinor vector algebra. Remember we did a lot of vector analysis with complex numbers. Well, now we're going to do it with spinors. And then finally, this whole thing about operators, we call it the crazy thing theorem. We've got to get that thing down. So there's a little bit of craziness in this. But then Hamilton was crazy. Let's just face it. He's a genius. Okay, and geniuses are crazy, right? I'm not a genius, but I am crazy sometimes. Anyway, the idea is I'm going to expand this matrix in terms of matrices that you've already played with, I'm sure, in elementary quantum mechanics nowadays. And that is, I'm going to take the A and multiply it simply by the matrix that has a 1 in the upper left-hand corner. I'm going to put the D on a matrix that's just like that in the lower corner. And then I've got these two guys, B and C. Okay? So I'm going to have here the 3. Now this isn't Hamilton, this is Pauli and Jordan. These are the Pauli matrices. This one is actually called sigma z, this one called sigma x, and this one called sigma y. We use A, B, and C because we've got mnemonics for this, and we've got physics to connect to this. This one is obviously asymmetric diagonal. It's a diagonal part of a matrix, and it's asymmetric if these parameters aren't equal. So that's why we put an A minus D times this guy, and then an A plus D sort of sits outside of, this is the thing that is a unit matrix that you would normally throw away in quantum mechanics if you weren't doing information theory, which requires you to know the phase. In any case, there are two others. This one right here, B stands for bilaterally symmetric or balanced. And then C, there's a lot of things that go with C. It's chiral because it puts handedness on things. It makes circular polarization, so C for that. It is complex because it involves this guy, it's imaginary. It has effect on Coriolis things. Anything that has to do with rotation of a system will experience that. We will also have cyclotron motion. It's curly. It's made different between a state that's a standing wave and one that actually moves. And a wave that moves is a current carrier. So lots of C's to go with this one. This one, I put the color here to be green, as in a traffic light that says go. And then this one is sort of a caution. And then this one, it just stops you. That's the one that makes standing waves. So these are best known as Pauli operators, X, Y, and Z. B, C, and A for us. Okay? So this goes back to 1927. That's way in the future for Hamilton, who was actually inventing these things a completely different way. Just looking for an algebra that could take complex variables into this third dimension. You could only do two-dimensional fields and things like that. Well, he's thinking of finding something that he could replace the I with that would have ability to go to 3 dimensions. And he kept looking for 3 things that would work until one day he realized he had to have 4 things, and those are the quaternions. So if you take the ordinary I and multiply the Pauli matrices, X, X, Y, and Z, X, Y, this is the Y and this is the Z, or I, J, and K is what Hamilton called these operators. These are operators that all square up to -1. This one, and this one, by putting the I on there. Whereas Pauli doesn't want to square a -1, he just wants to square a +1. So those are what Pauli's operators are. But other than that, they're the same as Hamilton's. The I factor makes that difference. Okay. One of them is Hermitian, the other is anti-Hermitian. That's our language. Okay, so Hamilton quaternions square to -1, like an imaginary number, and they make up the complex theory that he wanted to have. They make up what's called a quaternion group. They multiply with each other and make a group of order 8, but we won't need to use that for what we're doing here. Now, if it's just asymmetrics thing here, A and D with A, let's see if I've got that. In this particular case, say A is less than D, then as I make A and D not equal, but still less than B, I get something like this. If I make A and D equal, but less than or greater than B, I have something like this. And we'll be looking at those guys. None of this involves this chirality guy, okay? But we can easily add it, as you'll see later on. Okay, see if there's anything else I need to say about that. Here's the same thing shown in darker colors. I think is this making sense so far? Okay, any questions? This is a good place to do it. Okay, now the arithmetic of these things. What's the arithmetic that matches what happened with the complex numbers? Now, just to see what it is we're trying to do here, is we're trying to figure a way to easily evaluate and as I say, most important, visualize this solution to Schrodinger's equation, to our first order oscillator equation is what we're really talking about here. So we're looking for an easy way to take an exponential of that H operator, actually I times it, or minus I times it, so it fits the physicist's phasor way of viewing the oscillatory motion. So the idea is that we're going to do in e to the I all of this stuff. So all of that stuff is in an exponent. We've got to figure out how do we make an easy way to just get that thing for free. Now we know that we can take, with our spectral decomposition, we can take a exponential function, no problem. But it is a problem in the sense that it takes several steps. We want to visualize that. We want to see it right in front of our eyes. At least I do. Okay? And I think you would agree after seeing this that it is a wonderful thing that happens here. So we're going to have different ways of looking at this thing. Most of them will be factoring out an overall phase of omega 0 time. That's called the dynamic phase, and that's this contribution right here. It's just got a unit matrix in it which commutes with all this stuff, but these guys don't commute with each other, so they go together in a sum of three things which has a dot product. Now we'll come back to this and we'll give meaning to these numbers that we're talking about here, namely B, C, and A minus D over 2. The A plus D over 2 that goes with this one, that's easy. These are the ones that we have to figure out what they do and what they look like in some sort of graph. So this is going to be sitting here as we do our manipulations to get to understand this, the exponential. Okay? So the symmetry relations of A, B, C are key. And the quaternions, which have actually a minus I attached to Pauli's operator, either way, it's very powerful. Each one of these sigmas squares to a unit matrix, whereas, as I've already said, each of the quaternions square to what Hamilton wanted, a generalization of the I. This is true for spinor components based on any unit vector. Right now we've got a spinor component based on X, or what we call B. We've got a spinor based on Y, which is we call the C. That's the weird one, chiral one. And then we've got the diagonal guy here based on Z, or A, the totally asymmetric on the diagonal guy. But we can take a vector that's any combination of those three and have the same thing. This is what was the aha for Hamilton when he realized that if he took four things, included the unit, he could have an algebra that was closed and very simple. So just take a look here what we do. We take sigma dot A, and that's the symbol for some of these dot products in here. It's a weird thing where one of these things is a vector of matrices, X, Y, and Z, and the other one is just a plain old real vector, a unit vector in particular for now, AX, AY, and AZ. So these are numbers, these A's, but the three operators that go with X, Y, and Z are the matrices that you see up here. There's not color here. Okay, so, and then I take the product, the square of that, and I get all, well, it looks like a big mess here. I got 9 things, but then I realize that when I have this, for example, XX and YY and ZZ, that's just 1. So I just get the vector back again, X squared, AY squared, and AZ squared, and multiplied by unit matrix. Well, what about these off diagonals? There's 3 things here and 3 things here, 6 things, and that's an even number. So wonders of wonders, if I do a dot product, dots don't behave very well, so once again I missed that. This is sigma Z times sigma X, this matrix times that matrix, gives me this thing, which is I times sigma y, but if I turn them around, do x after sigma z instead of before it, I get minus what I got here. So that gives me this sum of squares of the components, but this one cancels this one cancels this one cancels this one. All we get from this is this right here. And let me go ahead on the screen there so that's all being seen here. They cancel perfectly, leaving me with sigma a component, any component, not just x, y, and z, but any component of sigma. Take any vector you like, make it a unit vector, because that's what you do with x, y, and z, right? Little hats on them, okay? So this thing squared is a unit matrix, no matter how you do it. That's the aha right there. And he was so excited about this that he began carving the relations like this into a piece of wood that attached to a big bridge in Dublin, Ireland. And it sat there for years and years until finally people realized how important this was, what a breakthrough this was. This is as big a breakthrough as the one for complex numbers. This is super. This is huge. Okay, we haven't finished it yet, but he already knew he could finish it. So this is going to be a generalization of something that we have already looked at. And the way to see that is to take the product of two different general spinners, one that's got the vector A, another one's got a completely different vector B, and put them as a product. Okay, so here's the same deal. I get 9 things, but now there's not necessarily going to be any cancellation because this guy is very definitely different. If I have different B coefficients from this one, this is different from that one. So we're going to get something from all of those, as well as this thing right here, which will just be the dot product of the vectors A and B. Well, you probably have guessed already that the things that we get for the x, y, and z here are the cross products of the vectors A and B, to make a long story short. Okay? So that's what happens if you look through the algebra of this thing. Now, we're going to write this product in Gibbs notation. Okay? And I should point out, if you've ever wondered where Gibbs got his unit vectors I, j, and k, this is where he got them. That's the notation Hamilton used for operators representing coordinates x, y, and z. But Gibbs says, you know, people back in America, they're not as smart as these guys over in Europe. So I got to do something to simplify it. And that's where we get it in every calculus book. I, maybe with a little hat on it, right? It's just a vector, right? But we're talking about operators now today for that. And Hamilton definitely was thinking of that too. Now what's this a generalization of? Remember in chapter 10 of the unit where I did an A star B, right? And you take a complex conjugate of an A. This is only 2 dimensions, x and y. And you leave the B alone, and then you put them in a product. You get the dot product of A and B here, and then you get that weird truncated cross product, right, with a magic Z that was out of the plane, right? Here we get that exactly. So this was an important identity. This is the result where he realized that he had succeeded in generalizing complex numbers to 3 dimensions, actually to 4. What we're able now to do is relativity with this as well. That's where it really gets powerful. We'll have very little talk with that here, but in other courses I teach. Anyway, Hamilton is now able to generalize Euler's complex rotation operator. That's what he's able to do now. We have to see that before we get to work on this. Well, there's the thing that comes out of chapter 10. Remember, we have the wonderful cosine minus I sine, the minus coming because we're taking the minus exponential, just like we do with quaternions from now on. Okay? And the deal here is that the even powers of this thing are plus and minus. Odd powers are plus and minus the I. So you have this relationship, which is going to be happening with the quaternions too. Just have to arrange them correctly. So that's the thing that's going to make that identity down there really work for us. So we're going to be able to go through and 0th power, 1st power, 2nd power, 3rd power, the 4th power is back home again. And we just continue with our powers, just like we do here, in order to make this term, and then this term, and then this term, and then this term. Now you start over again, do this term, that one, and so forth. It's a well, quaternion. It's four things that you go through each time you cycle through the series. Okay, so that's really what it boils down to. This, e to the minus I, some number, angle usually, is just 1. Usually we can write the 1 for this one, and then minus I times sine. Cosine, and then minus I times sine. Here it's going to generalize. You've got to write the 1 now, because you've got to remind people that's a unit operator, but then this is the same, except that you've got 3 possibilities here for this. This has 3 components, this guy up here. This guy up here, the exponent, has 3 components. This guy sits outside of the whole thing. It doesn't mess it up, because the unit operator commutes with everything. But these guys right here, those are what we're really looking at. Okay, so here's the notation that you see up here. When I write sigma sub phi, I mean a sigma that is married to a vector that points in some kind of direction phi, using Greek letters, and then the actual number that goes with it. Okay. And I have written that as sigma dot, then the vector that we're really representing here. Not a unit vector yet. I have to divide by that phi to really get what I want, and that's what's going down here. I have to multiply this thing by phi, and there's the unit vector. Most of the time we get to just work with the unit vector when we play with these things. Minor detail, but we'll get to it soon enough. So that's the generalization. Now, I like to commemorate this discovery because it's more general than this. I call it the crazy thing theorem. If you've got something, you know, it kind of looks like somebody I know that's really crazy, our president. This is Trump squared. If he's -1 when you square him, then you can use him to make a rotation operator. That is, e to the crazy thing times some variable, could be complex even, but let's just say it's real. E to the crazy thing times phi is equal to the unit operator, that unit operator, whatever it is that you're working with, times the cosine of the parameter, and then the sine of the parameter times the actual crazy thing. Okay? So far, we've been dealing with crazy thing minus I. That's what we've been dealing with in the complex analysis. But that's only 2-dimensional. It doesn't take you very far. But minus I times this guy, which is 3 terms, these 3 terms right here, you can tack that on if you want, but we usually leave it off. And that's this or this, the unit guy. You have to divide the dot product by that, whatever the length of that vector phi is. That's what we call the crank vector, and we'll give it a better notation than visualization shortly here. But that's where we stand right now. But obviously there are things called octonions and other stuff that you can use as crazy things. Trump is not the only crazy in the world, although it may seem that way.
And that's only an opinion.
Yeah. Well founded.
One of us, not both of us in any sense.
He may be off the scene fairly soon, we can hope. Okay, so here's an example right here where I just use a sigma A, which is a diagonal matrix. So if I write this e to the minus I, that's my crazy thing, so I do a cosine times the unit and then attach the crazy thing times sine. Well, we've already seen that. That's just e to the minus I phi and then plus I phi. This is our z rotation right here, using Pauli's notation. This is our asymmetric diagonal A rotation for our crazy notation. Here's one that you recognize right away. This one is a crazy thing made out of that crazy C. Go right to the most crazy one, okay? And simply plunk it down here in front of the sign, the unit operator times the cosine, bingo! You've got a rotation matrix that you already know about, right? Except it's in spin up and spin down space. It's in this weird two-dimensional complex space. You see, that's cool. Okay, I'll let you work out the X or B operator yourself. It's very similar. Here's the whole thing just done. This is what it looks like. If I've got all three parameters lit up, phi A with a hat on it, phi B with a hat on, using a unit operator, a unit vector to define it, okay, and then multiplying by whatever that value is, but you don't have to do that for this relationship. I just put cosine and sine of that parameter, and I get this. So this is a matrix that's going to be our Hamiltonian. You're going to be able to solve any two-level system with this, regardless of how many C stuffs you have in there. It just that's where the C component goes, and then the B component sits here with an I, and then the A components sit here, and we've thrown out this guy. Okay, so this is a picture here of what we're really interested in, and then we will have an overall phase based on A plus D over 2. Can't throw that away if you're going to do information theory, but most of the other quantum mechanics up to the development of information theory didn't really care about the overall phase. It's something you can't measure most of the time anyway. Okay. All right, so that's the main result that we're going to take to the, hopefully take to the wars with us, and make a marriage between quantum and classical. So as I say, this is example 1. Example 2 are really rotations. I want to test these operators by making them rotate each other. They can do that, right? By just simply multiplying fore and aft. In order to rotate a matrix, you have to work on the kets from this side and work on the bra parts of it this way. So that's what I mean by fore and aft, which is a Siemens jargon. Okay, so I have this thing, this vector here with the 3 parameters for a unit operator. That's what I'm going to be playing with. So if I want to do, for example, a C rotation, a rotation around the C or y-axis. Okay, so this axis that we're going to color green because it is associated with a chirality or rotation. I'm going to apply that operator to this operator. That means I'm going to take this rotation matrix that we just got by the crazy thing theorem, and I'm going to attack this one, fore and aft. That means I have to put the formation conjugate over here. That is the inverse of this operator over here to work on the other side, the bra side of the components in here. Well, I go ahead and multiply them. At first it looks kind of messy. I got quadratic expressions, of course, for the sines and cosines, but then you recognize them immediately. As the diagonal element has cosine minus sine squared, that's cosine of 2 times the angle. And this one on the off diagonal is a sine of 2 times that. Well, that turns out to be exactly what the vectors do. They break out into a sine and a cosine component in x, and z. So this is a rotation around the y. You get something that's a linear combination of x, that's b, and z, that's a. Z or a, y or c, and then the b or x axis is right here. In the disk of rotation, you have to imagine that disk is out of the screen a little bit there, getting rotated by whatever angle. In this case, I've got theta c equals 30. That's this angle right here, and I'm going to do 2 times that, so it's really a 60-degree angle that I rotate. And that magic 2 is really, really important. Okay, now, once again, the notation for that unit vector, that's this thing. It's got the magnitude of this vector being divided out. Now later on we use angular momentum, angular velocities to describe this thing. But if it's a unit, it's the same vector. I just have to make sure I divide by the sums of the square rooted of whatever I'm using to describe that vector that goes in this. Okay, well, it's getting a little hairy here. This is kind of weird. The idea of having to do a rotation fore and aft and ending up with something that is vector behavior. Okay, that is ending up with this matrix times this matrix times this matrix. This is the inverse of that. Fore and aft gives me this, you see, a cosine and a sine of the thing. Now, here's A getting the treatment, here's B getting the treatment, basically the same, except that cosine sine here is sine cosine here, and this one has a minus sign on that. So we really are getting both the rotation of what was originally the A and what was originally the B, that is what was originally the Z component and what was originally the X component, by a C rotation, which is the y-axis perpendicular to A and B, or Z and X. Okay, so far so good. And now I apologize, Millie, I'm sorry you had to do all of the hospital thing. You're probably completely snowed by this, but that's what this camera is for, and the batteries have not run out yet, so even if it does, you've got this part of the lecture to look at. Okay, but you can sort of see some of the things that make this work. So we're, like Hamilton, so happy to be able to handle the exponential of a Hamiltonian, because that is the time evolution. And we've got it married to classical two-dimensional oscillator, so we're happy there as well. And the problems that I've given at the end of today's homework are to do two ways with a two-dimensional. This ABCD way, and then the way you're used to, and make a comparison. But let's do a notational comparison here of the generator of the rotation for the two-dimensional guy. And remember that we also can look at this thing in the 3D vector space. We don't have to live in that weird complex two-dimensional space that we call spinor space. But when you do, it makes sense to move your factors of 2 around. That factor of 2 is so amazingly beautiful and also very mysterious and vexing that we have to point it out wherever it is doing anything in order to understand this stuff more clearly. Anyway, we've got the symmetry archetypes. This one, if I just leave it alone, I've got asymmetric diagonal matrix with a unit operator. Pretty simple, but still, that's really all we were doing with our classical operators so far. Although we do have an off-diagonal component when we put this. This is the bilaterally balanced component, the X component in our notation, the X component in the Pauli designation. And then the C here, this crazy chiral circular complex cyclotron, you name it with a C beginning it, that operator is complex off-diagonal. This one is real off-diagonal. Okay? Now, what can you do here? What has gone on here that makes these a little different? First of all, we talk about spin a half. I have to explain why spin a half has a half a spin. Why is it half fast? To be crude. Okay? It is. Things in spin land go half as fast as things in vector land. So what we're going to find is that the operators that we actually call S sub B instead of sigma sub B have a half. But to make up for that, I got to put a 2 out here in front of the B here. That is, I have to, instead of using this little frequency, it's half as fast as this one, I got to use this one. I got to use 2 times speed here. So I just move the 2 over. I put a 2 in the denominator here and put the numerator here. Same thing here. Same thing here. Okay? So A minus D over 2, this becomes A minus D. B becomes 2B, C becomes 2C. All right? That sort of makes sense. But the notation is different. I've got a big frequency here, twice this, and twice this here, and then I've got a spin operator that's half of this, and that one's half of that. So that's worth remembering. This is sort of a chart to keep track of as we go back and forth between the space we live in, which is this one, roughly speaking, and the space that is hiding underneath what we live in. That's the spinor space. We're all made out of fermions. They're all spin a half, neutrons, protons, and electrons. So that's what we're dealing with here. This is a lot more than classical mechanics, but it's also classical mechanics. It's wonderful things you can do in classical mechanics with this. So the so-called Jordan angular momentum operators, they usually are labeled J for Jordan, but we're going to name them all S for Stokes, because Stokes got this stuff shortly after Hamilton discovered his quaternions. Stokes did his Stokes vector, which is down there on that far screen, in 1867, about the time we were finishing up the Civil War in this country. And remember, Hamilton got his idea in 1843 and marked that bridge up, which later became a museum in Dublin, Ireland. Okay, so this is the notation for the spinor space exponentiation right here. Now I'm using the sigmas and I'm using these little omegas, okay? But that's entirely equivalent if I'll just shift my factors of 1/2 back into a place. I will get this. This is what we would use if we're thinking in a 3-dimensional vector space. So that's an important way, just to keep track of different notations that do have different geography, as we see. The spinor space definitely does. That thing about being half fast. So here's the crank vector. That's what this vector that drives, that's what this vector right here is. We saw how it rotated unit vectors. This is the general rotation now of any angle that you want. And this is the crank vector that is good notation for 3D vector space. You think of this as X, Y, and Z. We put them in the ABC order here. The same thing with that one. Okay, I think we're making progress here. If there's any questions about this is kind of all of the formalism. It's just a matter now of actually using it and then converting it a little bit so that it makes physical sense. And that's begins with understanding the mysterious factor of 2, at least a little bit. We need to do that before going on here. Okay, we're making progress. Now let's give a real down to earth explanation of why we have this factor of 2. In your quantum mechanics, you would actually make a graph to describe a spin space by maybe drawing a little ket for the spin up state, and then maybe another ket that had an arrow pointing down to indicate spin down, right? Okay. Now, what I would offer you right off the bat here, and that's why this analogy with the 2-dimensional oscillator is so powerful, what I would offer you here is to use the polarization view, which is kind of on that screen over there, where you have X and Y. Down at the bottom there is the polarization XY space. That is spinor space. That's Stokes' spinor space. John Stokes, okay? 1867, published. Not a picture like that quite. He hadn't really figured it all out yet. But it's pretty close to what he'd agree. That was a good picture of what he did. here I would put an X, and here I'd put a Y. And at that point, the mystery can be solved completely. But you can kind of use this one to say, you know, you gotta have to do this half-fast thing. We're gonna have a 2D spinor space that is half-fast. And that's because when I do rotations, and those rotations are actually carried out in the vector space in which we're used to living, going from spin up to spin down is a 180-degree rotation, indicated right here. This vector starts out at 0, 0, 1. That's the z-axis. We're now using Pauli notation, okay? Instead of writing B, C, and A, we're doing it like you're used to. And there's the operator in 3 dimensions, nice real 3x3 matrix that will rotate you by some angle beta. Here it's pi over 3. I've gone out to 60 degrees. Here I've gone out to pi over 2. That's 90 degrees. Here I moved all the way by 180 degrees. So I have spin down now, right? Spin down means minus there instead of plus. What's been going on in spinor space during that period? Here's the matrix that rotates the thing around the y-axis that we just calculated. And I'm using angle beta, Euler angle beta, and that notation is what we're going to use, so we're going to start right now. And do the rotation, get cosine and sine beta over 2 for beta equal to pi over 6. That's beta over 2, right? So that corresponds to this thing, which has beta of pi over 3. This one has beta over 2. That's the way you measure in this space, half-fast. But to make a long story short, spin down is only 90 degrees away from spin up. It has to be half-fast from that point of view, or you don't have a space that behaves right. Now this one will be complete if I do it again. It'll bring me back home, right? But this one will be going half-fast, so it's going to end up over here. And that's what the next slide is. Okay, I'll put it right there. There's spin up was where we have now what we're doing is we're just continuing our rotation from what we ended up with here, and we go that, and that. We end up back with spin up, but it's minus spin up. It's on the other side. It's out of phase. These are all waves, so that's really important. And we'll see that happen with our oscillations. That's when you really understand how this 2-to-1 business works when we apply this to our 2-dimensional oscillations as opposed to the very abstract thing called electron spin or neutron spin or proton spin. Okay? So this is just getting a little bit of a clue of what is involved with this thing. So, halfway home in spinor space. This one's all the way home, okay? It's got the thing back at spin up, which is what we started with. Okay. So, spinor space needs 720 degrees. That's not just 2 pi. It needs 4 pi to come home. And we're going to show you a lot of things that behave like that. That's where things get weird and where you have to deal with the... But in the meantime, let me take us back into vector space and just talk about, well, hospital stuff. We just come from one. The idea that one of the real lifesavers is to be able to just wiggle the proton spins in water and completely read what's going on in your body with respect to, you know, water, right? This is, you know, what a gift the physicists have given here, okay? Nuclear magnetic resonance. Now, we don't call it nuclear magnetic resonance because everybody's afraid of nuclear, right? So it's called MRI, right? Magnetic resonance imaging. But this is what we're dealing with here. You see, we've got, now I'm doing X, Y, and Z, but we got a matrix like this as our Hamiltonian. It's just M dot B, okay? magnetic moment, basically G times sigma. The sigma operators, X, Y, and Z, are just sitting here, here, and here. Put them all together, you get this. Okay? Or this is the notation we've just been using with the Pauli XYZ notation thing. So there's your omega dot sigma right there that we've been playing with. Okay? And here are the three colors that I assigned to the thing that makes you curly, circular, complex, and current carrying, to things that make you standing wave either on the diagonal or on the, or off diagonal or on the diagonal. So that's the well-known spinor operators, and what do they do? Okay, what do they do? What does this crank that's generated by a magnetic field? That's this thing right here. So there's a B vector, which we're going to call omega, big omega. This is when you look in vector space, you need to use the big omega, not the little omega that we associated with doing things at half-fast in spinor space. Okay, so it's really easy to see what a Hamiltonian does. You push your Hamiltonian down, it means you put down a magnetic field. 12 Tesla, right? 12 Tesla is sufficient if you happen to be carrying a knife or a wrench or screwdriver in your pocket and you walk into a 12 Tesla hospital thing, it's going to rip it out of your pants and hit the magnetic instrument so hard probably you'll destroy it. I mean, that's the kind of field you're talking about here, okay? And then you have a little tickler field, which is what this is, the little X field here, or Y, that resonates things. What an amazing piece of equipment. Ends up reading out a sharp image of what's you got in here that they can go and fix, hopefully. Okay, now, I think at this point, it was worthwhile in the last 10 minutes or so here to switch over to the other lecture. But I can continue with this one probably pretty well for a while here. One of the things that I want you to get familiar with for a couple of reasons, because we're going to do rotations later on, but mainly I want you to get familiar with for how we do rotations that reflect changes of vibrations of 2 dimensions, the original problem that involved the K matrix. So you've probably all seen Euler angles in what I call the astronomer's diagram, where they measure the thing from a horizon. It's amazing how physicists are, you know, habit freaks. Once they see a diagram that somebody's given, and it makes sense to have a horizon, measure things in the sky from the horizon, because that's where they rise and set. It really does make sense for astronomers. But then seeing what those rotations are as, you know, really physical things and coordinates that you would use to aim a crystal in your laboratory. We call them gonometers, I think. Weird name to have. But this is what we've got sitting here, right here. And there are only 2 of these in the world. One is at Gila Institute of Laboratory Astrophysics. They don't go through that name anymore. They just call it Gila. Let's go the Gila Gorilla. And it's this thing is in storage right now, as I found out from one of our visitors, Jen Hu. But he's thinking about getting it out now that he knows how useful it is. But the basic idea is you start with all of them 0, and starting them with all 0 would be roughly equivalent to that. But there's another angle down there that you have to worry about. And where you put that is important. Usually I put it on the minus y-axis right there. And now if you read these dials when you're set like that, they should be all close to 0. Okay, so that would be 0 for alpha, which is the bottom angle. That's what you normally call azimuth. You can think of a Greek A, and you've got azimuth, right? And then you've got this angle here, beta, okay, tips the thing, right? So I start with this thing pointing up, and now I can aim the azimuth, and then I can point at you just by adjusting the 2 of them, right?
So the beta rhymes with theta from your polar coordinates. So alpha, azimuth, usually phi, right? Well, we're going to use alpha because we got another azimuth right here. This is the azimuth used by the aliens that live on this globe here. Okay, they see that as their azimuth, right? They share beta with us. Get the sign wrong. We think it's right, but they say we're wrong. Okay, and then they see this as a mystery angle. It has to do with our phase. Okay, so this is a powerful little machine that we've got right here, and several Nobel Prize winners have said they want one, and Dudley Hirschbach is one that might be paying for it. So we may be able to mass produce these things. By mass, I mean making 3 or 4 of them. Okay, so in any case, that's just the angles themselves. Now the operator that controls it is a whole nother story. Also 3 angles. It has an azimuth, okay. It has a theta angle, which I usually use in italic thetas to show that. And then, if you attach it, it has a 3rd angle that makes this thing rotate. And all of the angles change, you see, when you do that in a very complicated way, which is what we're going to be talking about next here, or at least begin to talk about. Okay, so that's the deal. Now, one of the things that this helps you understand is that if I start on the c-axis here where everything is 0 and swing that thing around so that I have the ability to rotate here and then swing this thing up to the zenith and rotate here, and that's all I've got to rotate with. And think about it in terms of the matrices that we have here, what that means. I back up here just once to show you. This matrix is diagonal and real. So Z is really easy to use algebraically. This matrix is off diagonal, but imaginary. Okay? Well, when I go e to the minus I times this, I get a real matrix. We've already seen the cosine sine matrix that comes out of that. Whereas if I put this in a diagonal, I just get phases on the diagonal, plus phase and a minus phase. So these two are the easiest operators to manipulate algebraically. So they're the ones that we get to use. That's it. That's what we're going to be rotating. We're going to rotate by beta. That's this dial right here. And we're going to be rotating both the gamma and the alpha in the right sequence. So that's what is shown right here. This is how you set a state with operators, with Euler operators. The Euler angle operators is what they really are setting. They're setting the dials on this machine. So there's no argument about, who's reading what. This is a machine where you should look at it to see what the Berry phase is. There are very few people, including Berry, that really can say what it is. Berry loved this machine when he saw it. The first I built it at Georgia Tech when he visited. So he's another one that wants one of these things. Anyway, the first thing that you do is set the phase. Because with this thing lined up, you're not going to see this dial underneath one of your cranks. You only have a Z crank and a Y crank. There's the Y crank, which happens next. You first set this dial right here, then leave that thing alone. It will automatically stay alone if you attach the suction cups and turn this one to whatever setting you want. And then the last thing you do, this is on the left, and we're imagining a vector here that's being operated on these three, by these three. This is the last one you do. That sets your azimuth. What the aliens see is the overall quantum phase. Just kidding. But in a sense, it's true. Okay? So, this is the product order to get that operator and to get the state alpha, beta, gamma. Okay. So, let's just do it. Here's a matrix that is the three-dimensional, has in this one, the three-dimensional matrix that describes a rotation around the z-axis. And here's another one that's around the z-axis, but it's alpha this time. Okay? And it's alpha right-handed We're using a right-handed notion. This one right here is also right-handed, but if you remember, these things cycle, so the minus sign comes out here for beta. So when you put all of these guys together, you get a 3x3 matrix that kind of looks a little bit complicated. And that's what is shown over here as well on the brighter screen, but this one has better color. Okay, so we're talking about the columns here as the vectors that describe kind of what you're going for. There is the EZ vector right there, and look at that. That's just polar coordinates, right? Cosine alpha, sine beta. Sine alpha, sine beta. And then cosine beta. Okay? So that's EZ bar, the vector that lives with the alien, so to speak. And then Y bar and X bar, those vectors are a little bit more complicated. So that's the lab frame polar coordinates of the Z body vector in general. Using Euler angles, which are dials, you see. They're dials that are attached to that thing. There's no worry about commutativity once you specify the order of these things as alpha, beta, and gamma, which is the alphabet order for Greek letters, alpha, beta, gamma, so it really does make sense in English as well as the thing. You should notice, though, if you're looking at the original vectors that are in the laboratory, as seen by the aliens on the body, it's also polar coordinates if you just put a minus sign on the angles that we're dealing with and use gamma for their azimuth. And you see it's minus because of this sign right here. This one is plus because this sign and this sign are both minus. And the cosine doesn't care about sign, so it's positive. So this is the body frame polar coordinates. Kind of spooky, but you've got to think about what's inside something you're playing with as well as what's outside. Okay. I think that's it. In any case, this is just sort of a picture of this stuff all together. I don't think there's anything more I need to say. The body frame view using the gamma and the beta with minus signs, and then the lab frame view using what we're used to, alpha and gamma, that's phi and theta. And the other gamma, well, it's the quantum phase as it turns out. Okay, now when it comes to doing a spinner, you start with the original spin up, and now we're talking about spinners, so we're going to be talking about 2x2 matrices. We're going to do the same order here. A gamma about Z, a beta about Y, and an alpha about X. Okay? Now it's not quite that simple because our Z is called A, our Y is called C, and our X is called Z, our A is called Z, so we have to be careful with that. But aside from that, this is the way it looks. So you take those matrices and multiply them and apply it to a spin up. The spin up is just a two-component, has only the first component with an amplitude. I'll call it amplitude A, but you normally normalize that and it'd just be 1 there. And then here's this matrix right here, but you see the only thing that's going to count now is this guy times that, forget that. This guy times that, forget that, right? It's a 0 here, okay? So the effect is the gamma here, that's minus gamma, minus gamma, there's a minus sign right on the gamma, that's going to factor out. So there's the overall phase of the spinner, and then here's the relative phase, which is, has various names. It's called a coherence, or there are kind of other names, I think. So alpha, the difference in phase between these two, which is alpha, is a key angle. That's one you easily observe. This is much harder to observe. That's why quantum information theory is having a problem. It's because the overall phase is very squirrely. Okay, so that's the key thing. And I think we should probably end with just this slide right here, and then we'll come back and on the next lecture, we'll go for the other lecture, which has a review of what we just done, and then we'll get going with this. This is where you take actual expectation values for a particular amplitude, two-dimensional amplitude. Now remember, the two-dimensional amplitude for us with our classical oscillator is x and y, p sub x and p sub y. The ones and twos are x's and y's, not spin up and spin down. Much more physical, much more visualizable. So we're looking at a complex amplitude for the first component, a complex amplitude for the second component, and we're going to plug that in and actually take an expectation value like you do in quantum mechanics. And we get, for our classical system, operators that may or may not be constant during this. If I don't have any perturbations in the C, this is an angular momentum in the plane. X py minus y px. Okay, so that's a typical, that's what I call chirality in the oscillator. The oscillator will have chirality. And then balance. Is it balanced with respect to, well, that would mean that you have a equal masses and just a coupling between them that makes you have the same components in the upper right hand and the lower left hand corner of your diagonals. That is a weird invariant thing, and I call it balance for B, okay? And then A, asymmetry. That's also something that can be conserved. That is the difference between the kinetic energy of the x's and the kinetic energy of the y motion is constant. Anyway, these are possible invariants that help you solve weird problems with the oscillator. And they're nothing but polar coordinated alphas and betas. This is the, right here, the chirality, that's the y right there, C it replaces the y, okay? And then there's the balance here, that's the x, okay? So this is x, y, there's z. Multiplied by a half now. The amplitude has that 1/2 in there in order to make all this work. So this is really important. These are, you know, things that you need to know if you are going to work in information theory, because you have a way to visualize it that's much cleaner and more close to classical intuition than other things. So that's what we're talking about here. So we're going to have ellipses with different angles and things. They're going to be the polar angles of the spin vector in the three-dimensional space, and that's what that thing on the far screen there is showing an example of. So you're learning another field by doing this, not just the simple quantum mechanics of two-level systems. It's not simple, but we can make it simple. But also polarization dynamics and action. Ellipsometry, they call it. This is really powerful kind of spectroscopy that's just now being really used because we have such, you know, good optical devices that can handle it. Okay, so we'll take on this on Thursday, and some more mysteries I hope will be revealed. Tune in, watch this space.